All right, folks, we've come to our Unit 10, Thermochemistry. We're going to be talking a little bit about the transfer of heat to begin with, which is not thermochemistry per se, but I think it's a good place to begin. You'll see this a lot more in physics next year, but I think that's a good place for us to start. So let's talk a little bit about what we mean, however, by thermochemistry. Well, the prefix thermo really gives it away, and that is that it is the heat of chemistry. And as it turns out, it's a very important field of interest, particularly now because of the fact that humans have been using fossil fuels for thousands of years, but we're very quickly depleting our resources. And this is causing tension between nations because of the fact that there is a power struggle over control of these fossil fuels. And we're going to be having to look for alternative sources of energy other than coal and the other forms of energy that we've been using over the past several thousand years, right? So the point is this. The point is that thermochemistry means the making and the breaking of bonds and the energy that is associated with them. So reactions happen when molecules bump into each other. We know that. But bonds between atoms in these molecules hold energy, which is released when the bonds are broken and energy is absorbed when other bonds are formed, right? So if I have a theoretical situation where I have, say, A, B breaking into A plus B, there's also a heat component associated with that reaction. In other words, heat is either absorbed or released, right? Generally speaking, if a bond is broken, the energy is going to be released. Now, in the example of N2 plus H2 yields NH3, let's take a look at the N2 molecule. Nitrogen gas, or N2, is a triple bond between two nitrogens, right? And hydrogen is a bond between two hydrogens, just like that. So in order to make NH3 from this, obviously, bonds are going to have to be broken, right? The bond between the two nitrogen atoms must break in order for the ammonia molecule to form. 3 bonds between nitrogen and hydrogen must also be formed to create the ammonia molecule. So for ammonia, which is NH3, this is the Lewis structure for that, by the way. We have to create 1, 2, 3 nitrogen-hydrogen bonds. So there is a net release of energy. In other words, in the process of making ammonia from nitrogen gas and hydrogen gas, the bonds that are broken are releasing energy, the bonds that are made are absorbing energy, but there's a net release of energy. In any chemical process, if energy is released into the environment, we call that exothermic. Exo means out, thermo means heat, so heat released is exothermic. If the energy is absorbed from the environment, we call that endothermic, okay? Endothermic. So two important definitions to start the unit: exothermic versus endothermic. Let's talk a little bit about the measurement of energy. The energy transferred between samples of matter because of a difference in their temperature is called heat. So for example, if I have a piece of ice on my hand, I melt the ice. My hand melts the ice because heat is transferred, or energy is transferred from my hand into the ice. On the other hand, if I grab onto a hot skillet, the heat is transferred from the skillet handle onto my hand because there's a temperature difference between the two. That's what we call heat. So heat is often measured, is often called the lowest form of energy, the lowest form of energy. In this form, it is easily measurable by determining temperature changes caused by the release of absorption of heat in a chemical process. So in any chemical process, there's going to be a transfer of heat, and we want to be able to measure that transfer of heat. Now, I want to go back to something that I talked to earlier in this lecture, and that was the idea that there can be a transfer of heat without being specifically a chemical reaction. So I need to define a term that is very important to that process, and it's called specific heat. Specific heat is heat energy, or actually it's the heat required to raise the temperature of 1 gram of a substance by 1 degrees Celsius or 1 degree Kelvin. So with regard to a specific definition or a definition for specific heat, that would be the definition. Again, it's the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius or Kelvin, either one. So heat energy was originally defined in terms of the calorie, which is the amount of heat needed to raise the temperature 1 gram of pure water from 14.5 degrees Celsius to 15.5 degrees Celsius. By the way, this is not the same calorie that you think of when you say, for example, if you know of someone who's dieting and they say I can only eat this many calories per day. It's not exactly the same as this kind of a calorie. This is a very specific calorie with a very specific definition. The joule is the metric unit for energy. 1 calorie is equal to exactly 4.184 joules. This quantity is known as the specific heat of water. So water has a specific heat of 4.184 joules per gram per degree Celsius. Specific heat of water is 4.184 joules per gram per degree Celsius. Okay? The following equation enables chemists to determine the heat energy of any process by measuring the change in temperature of a known mass of water, right? The units used to measure heat are joules or kilojoules. So this is the formula. It's right here. Heat energy transferred is equal to the mass of whatever's of interest times its specific heat times the temperature change. So this is it. And by the way, we call heat energy little q, small case q. So heat energy is equal to mass times specific heat times the temperature change. In this equation, Q, the heat energy, is expressed in joules. So heat energy in joules. The temperature change is always determined as the final temperature minus the initial temperature. So let's take a look at an example. How much energy is absorbed as heat by 20 grams of gold when it is heated from 25 to 35 degrees Celsius? The specific heat of gold is 0.13 joules per gram per degree Celsius. So what I've got is a gold ingot, let's say. And what I want to do is I want to measure the amount of heat energy or the amount of energy absorbed as heat. It doesn't matter where the heat is coming from, right? Heat is being absorbed by the gold from somewhere. It may be water, it may be the atmosphere. It doesn't matter where it's coming from. The question is, how much is it, right? So we'll use our formula. Q is equal to M times C times delta T. The mass of the gold ingot, I'm told, is 20 grams, right? Pay attention to, by the way, the significant digits. That's 2 and 0, and both are significant because zeros to the left, trailing zeros are significant. If there's a decimal point, there is one, so it's significant. So 2 significant digits there. Times 0.13 joules per gram per degree Celsius. Again, 2 significant digits on the 0.13 times 35 minus 25. Remember, it's final minus initial. We're going from 25 to 35. So 35 minus 25, 10 degrees difference, right? When we multiply these across, we get 26 joules. So 26 joules of heat energy then are being absorbed by this gold ingot, all right? All right, very good. Let's keep going. Let's take a look at another example. A 4.0 gram sample of iron was heated from 0 to 20 degrees Celsius, right? So we know the mass and we know the initial and the final temperatures now. It absorbed 35.2 joules of energy as heat. So they're giving me this time the Q. They're asking me for the specific heat of this piece of iron, right? Now, don't say to yourself, well, I just figured it out for gold. Not all metals have the same specific heat, right? So you have to recalculate for this particular piece of metal. We're going to use the same formula, however, and that is this one right here. Q is equal to M times C times delta T. In other words, this is a heat transfer equation. But we're going to rearrange it because of the fact that we want specifically to know the specific heat. So we need to know C. So we're going to divide both sides by M delta T. And by the way, delta T stands for change in. That doesn't, if you're in chemistry or physics, engineering, it doesn't matter. Delta is that triangle, and it means change in. Okay? So we get C is equal to Q over M times delta T. We're just going to plug things in now. Remember that Q is the amount of heat absorbed, which is 35.2 joules. 35.2 joules. The mass in grams is 4.0 grams. The change in temperature is 20 minus 0, or 20 degrees Celsius. All right, so that's the final minus initial temperature. So let's plug everything else in. We've got 35.2 joules divided by 4.0 grams times 20 degrees Celsius, all on the bottom. Notice 3 significant digits on top, 2 here, 2 here. So I've got 2 significant digits in my final answer, right? So the specific heat of this metal is 0.44 joules per gram per degree Celsius. By the way, I can write that a slightly different way. I could have written it like this: 0.44 joules. Some people choose to write it this way: grams minus 1, superscript minus 1, degrees Celsius minus 1. You can do that as well. All right. I think we've got time for one more example. Let's take a look at this one right here. It says an insulated cup contains 75.0 grams of water at 24 degrees Celsius. Now, a 26-gram sample of metal at 85.25 degrees Celsius is added. The final temperature of the water in the metal is 28.34 degrees. What is the specific heat of the metal? Okay, so let's kind of understand what's happening here. We've got a cup just like this, and it's got water in it. And we've placed into the cup a metal. Okay, so here's the metal piece. So energy is being transferred either between the metal and the water. Either it's being transferred from the metal to the water or from the water to the metal, depending on the temperature difference, right? So here's our solution. Here's how we're going to do this. As it turns out, the water was warmer than the ingot, than the metal. So we're going to say the amount of heat that was gained by the water, we're going to say plus because it was gained by the water, is equal to the amount of heat lost by the metal. And then we're just going to plug things in. Q is equal to the mass times specific heat times temperature change for the water equals minus the mass of the metal times specific heat of the metal times the temperature change for the metal. So let's enter in the data now. The water weighed 75 grams, and we know its specific heat to be 4.184 joules per gram per degree Celsius. The temperature change, now notice the temperature change and how we arrive at that. It's final minus initial. So we started at 24, and we ended up at 28.34. So the temperature change is going to be 4.34 grams of Celsius. The mass of the metal was 26.0 grams. We're looking for its specific heat, and the temperature change this time is a negative 56.91 degrees Celsius. Remember, it's final minus initial. Final minus initial. So we'll just kind of clean things up, and we determine the specific heat to be 0.920 joules per gram per degrees Celsius. All right? That'll do it for this problem, and that'll do it for this video. I will see you on the next one. Thanks. Bye-bye.